Today we're going to be talking about how to find the vector which is orthogonal to the plane. And in this particular problem, we've been asked to find the vector that's orthogonal to the plane, where the plane is defined by 3 points. The plane runs through 3 points, 0, -2, 0. 4, 1, -2, and 5, 3, 1. We've defined these 3 coordinate points as point P, point Q, and point R. Our plane passes through these 3 points, so we need to define the plane and then find a vector which is orthogonal to the plane. Now, orthogonal, if you haven't heard the word before, you can essentially think of as meaning perpendicular. Remember that perpendicular means 90 degrees to. The only reason we're using orthogonal is because when we're dealing with vectors, perpendicular isn't a technically correct term, so we use orthogonal instead. But really, the vector orthogonal to the plane is the same thing as the normal line to a plane in three-dimensional coordinate space. Now, when it comes to vectors and finding an orthogonal vector to a plane, the first thing that we want to do is define the plane as 2 different vectors. And the way we're going to define it is with the vector PQ and the vector PR. Now, I'm not going to plot these points accurately. I'm just going to plot 3 different points so you can get a picture of what we're talking about here. If I have 3 points, a point here, which we'll call B, and a point here, which we'll call point C, what I can do is define one vector. This would be the vector here, A, B, like this. Define another vector as the vector A, C, like this. We'll call this A, C. And if I can illustrate these 2 vectors, then what I do is just imagine that there are 2 dashed lines like this that kind of form the 2 other edges of this plane, and I call this then a plane. So I really only need 2 of these vectors to define a plane, and that's what we're going to find. We're going to pretend instead that these are our points P, Q, and R, like this. We're going to find a vector PQ and a vector PR. That's going to define our plane for us. So to find PQ, like this, all we're going to do is take our components of Q, subtract our components from P, and use the results as coefficients for I, J, and K. That'll give us a vector. So what we're going to do is say our X components, we've got 0 and 4. So we're going to take the one from Q and subtract the one from P. So we're going to say 4 minus 0. 4 minus 0. That's going to become the coefficient on our I component, like this. Then we're going to add to that the difference between our y components, so 1 minus a -2, 1 minus a -2. That'll be the coefficient on our j component there. Then we're going to add to that the difference between our z components, so -2 minus 0, and call that the coefficient on k. When I simplify this, 4 minus 0 gives me 4, so I have 4i. 1 minus a -2 is 1 plus 2, or 3, so plus 3j, and -2 minus 0 is a -2, so I'm going to get minus 2k. That is a vector representation of PQ. Now I want to do the same thing for PR, and instead of taking the components from Q, we'll just take the components from R. We'll get 5 minus 0 times I, plus 3 minus a -2 times j, plus 1 minus 0 times k, and when I simplify, I get 5i. 3 minus a -2 is 3 plus 2, or 5, so plus 5j, plus 1k, or just plus k. Now these are my vector representations. I can also just pull out the components or the direction numbers of these vectors, and I can write this vector as 4, 3, -2 when I take the coefficients on my I, J, and K terms. Same thing here, I'll take my coefficients and say that my direction numbers are 5, 5, 1. Now these are vector representations of PQ and PR. I've essentially defined my plane. Now the cool thing is that all I need to do to find a vector which is orthogonal to the plane defined by these 2 vectors is to take the cross product of my 2 vectors, PQ and PR. So my cross product is going to be PQ, vector PQ, times PR. Remember, we denote the cross product with this multiplication symbol of x, PQ times PR. This distinguishes it from a dot product where we have just the dot in the middle here. So I'm going to say that that's going to be my cross product. And for the cross product, remember in our first row of our matrix here, we have I, J, and K. We always put that in our first row. Our second row is going to be our vector PQ. We're going to take our direction numbers and we're going to say 4, 3, -2. Then we're going to take the direction numbers from PR and say 5, 5, 1. Now, if you don't remember from Algebra 2 work with matrices, what we're going to do is pull out the discriminant values here for I, J, and K. So when we're dealing with I, right, we have I here in the upper left-hand corner. We want to ignore the row and the column that I is associated with and focus only on the values that are outside of I's row and column, and that's this square right here. So we just take these values and we say that this is going to be equal to the matrix here, 3, -2, 5, 1. We keep them in the exact same formation that they're in this larger 3 by 3 matrix, and we multiply that by I. Now we're going to do the same thing with J and K. The only thing we have to remember, it's easy to forget, is that the value for I, the value of the discriminant for I, we're going to keep as positive, but J is going to be negative and then K is going to be positive. We alternate like that. So the sign on our discriminant for J here is going to be a negative sign. We write negative, and then J, when we take J here, we want the numbers outside of J's row and column. So that's going to be 4 and 5 and -2 and 1 here, and we're going to keep them in the same configuration. So 4 and 5 and -2 and 1 multiplied by J. Then remember that K is always going to be positive here, so we add to that what's outside of K's row and column. We have K here, and the numbers outside of K's row and column will be these 4 here. So we keep them in the same configuration, 4, 5, and 3, 5, and we multiply that by K. That's how we break this matrix down into its discriminant parts, so we just have these 2 by 2 matrices. Then how we deal with these, remember we always multiply the upper left by the lower right, so that value is going to be +3. Then we subtract the product of the upper right and the lower left. Well, -2 times 5 is a -10, so we get a -10 here. We always subtract, and then we've got that multiplied by I. So same thing here then, we're going to say minus, because we have this minus sign here. 4 times 1 is 4, minus 5 times a -2 is a -10, multiplied by J, plus 4 times 5, which is 20, minus 5 times 3, which is 15, times K. And when we simplify, 3 minus a -10 is 3 plus 10, or 13I. 4 minus a -10 is 4 plus 10, which is 14, so we get a -14J. And then 20 minus 15 is 5, so we get a plus 5K. This is the equation of the vector, which is orthogonal to our plane defined by PQ and PR. We can also write it as just its component values or its direction numbers, 13, -14, 5. That'll work also. And basically what we've said here is that we know that since the vector PQ times PR, this vector here, which is the orthogonal vector we found, because we know that that's perpendicular to both PQ and PR, that it's also perpendicular to the plane through the points P, Q, and R. Therefore, we know that this vector, 13, -14, 5, is perpendicular to our given plane, the plane passing through the points P, Q, and R.